Okay, so looking at where chapter 3, section 3 begins in the book, this begins on page 235. But I don't want to spend too much time in the book because I think we can do the problems in 3.3 without the material they present in this section. We've kind of already covered this in ways that I think are better and simpler in our introductions up till this point. But let's take a quick look here, and then let's see if I'm right that we could then go and do some problems from 3.3 ourselves. So what they want to do in this section is introduce the idea of what they call circular functions. But what they state about what circular functions are for our trigonometric functions is they say that we've defined 6 trigonometric functions in such a way that the domain of each function, meaning the kinds of things you plug into the function, the domain was a set of angles in standard position. And these angles could be in degrees or radians, as we've seen more recently. So then it says what they're going to do now is use the relationship between an angle and an arc length of S on a circle to define these trigonometric functions by a real number specifically instead of by an angle. But the real number they're using is just the radian measurement on a unit circle, which is how I sort of defined things earlier on. So if we look at this paragraph right here, it says when the radius has measure 1 unit, the formula where S is the arc length, which is equal to R times theta, simply becomes that S is equal to theta. And so that's the very reason that initially I suggested we just think of theta in radians as how far you are around the unit circle, because those are the same thing. So then it says, thus the trigonometric functions of an angle in radians found by choosing a point X and Y on the unit circle can be rewritten as functions of arc length S, a real number. When interpreted this way, the trigonometric functions are called circular functions. So this thing they're saying they're going to introduce the circular functions, that's just another name for the trig functions we've already been working with. And this is just another way to rename the angle theta in radians as an arc length instead of as an angle radian measurement. And so then what do they do? Just to look at the 2 primary ones here, and then we'll leave this. They define the sine of the arc length S, which remember for a unit circle, that's the same as the angle theta. The sine is equal to the y value of the point, which is the way I've been defining it all along. And if you take cosine of S, again, S is theta, so this could just be a theta, and that's the x value of the point on the unit circle. So I basically tried to define it this way all along to avoid all of this confusion. And now the book is giving us all this confusion. And to avoid it, I'm just going to point out that that's kind of what we've been doing all along. And now I'm just going to walk away and let's just see if the problems in this section can be done using what we've already talked about. So I'll pause here for a second before I switch over. Is there anyone who wants to ask a question about what we have right in front of us here? All right, so I do think this is kind of confusing. I'm trying to avoid that confusion, but it's still addressed because I know that this is what you'll see in the book and the slides. But let's just see if we can avoid this confusion by just saying, well, could we just do these problems without looking at any of this junk? So I'm going to switch over to my writing device here to see if we can look at some problems in a way where I can also write on them without using my mouse pencil, because that never works very good. So briefly, before we go to look at the problems, I'll remind us that the idea, which they had a little bit of a picture there, but just a reminder of the simplicity of this, is if we have an angle theta in radians or in degrees, that will correspond on a unit circle to a point where there's an x value and a y value of that point. Imagining that there's the y here and there's the x. and that we're going to say that cosine of theta is the x value of that point, and sine of theta is the y value of that point. So theta could be in degrees, but it could also be in radians. And if it's in radians, then the theta in the picture would be the length of this arc. That will be theta. And that's before, like, when we get things like pi over 6 and pi over 2 and things like that. Right? So with that in mind, with that idea of what these are, and the fact that we can just punch some of these on a calculator or look at triangles, what if we then consider homework problems? Okay, so this is practice problem number 1 from chapter 3, section 3. So it says to use the unit circle, maybe stretch this out a little bit, use the unit circle along with the definitions of the circular functions to find the exact values of the given functions when s equals -3 pi over 2. And then they have sine, cosine, and tangent. So how would we do this? So the first thing I want to point out, and I think I can do that this way. There we go. The first thing I want to point out is when they say s equals -3 pi over 2, again, the s is referring to the arc length on a unit circle of how far you rotated to the right or to the left from the starting point. And so you can just think of this as being the same as theta when theta is in radians. And so we would try to figure this out by thinking, where would that be on a unit circle? And so this is a negative angle. And so in a negative angle, I'm going in this direction from the starting point here when theta is 0. And I want to go 3 pi over 2. And so we want to remember that all the way around is 2 pi, because that's the circumference of a unit circle. And so this is pi here. And if I'm going in the clockwise direction, then that would be negative pi. This would be negative pi over 2. This would be 0 where we started, but when we come back around in the opposite direction, that's negative 2 pi. And so I get to basically negative 1.5 pi when I'm up here, negative 3 pi over 2. And we've had pictures of unit circles we've looked at that have all of these radian degree measurement angles marked out so that you can look these up on a circle too. So what this angle is telling us, negative 3 pi over 2, is that the angle went negative direction all the way around until we got to there. So that's theta in this case, negative 3 pi over 2. Oh, my negative got blended with my sign there. This is negative 3 pi over 2. And so we want this point on the unit circle. If we can find out where the angle of negative 3 pi over 2 goes to, or where that arc length on the unit circle would land, then we can know what the point is, and we can try to evaluate these trig functions at that point. Okay, so now to get the sine of that angle, that's the y value of the point. So what is that point up there? So that point is a 0 for x and a 1 for y. And so I would then give the y value of that point for the sine, and that will be 1. The cosine is the x value, so the cosine would be 0. And the tangent is sine divided by cosine, so the tangent would be the 1 value divided by 0. But you may recall that dividing by 0 doesn't work, so we would say that that's undefined. Now, you could also check each of these by simply typing them into your calculator. So to remind us of that real quick, I'm going to switch again, and I apologize for this, but here we go. So I'm going to switch this. So if I go over to the calculator, and again, I showed Desmos before, you can bring up the unit circle. You can put in like different kinds of measurements and you can see the points. You can type in values here of different things. But I can also just, for example, type in sine and then put in -3 pi divided by 2. So I could also evaluate, and then you can see the answer here is 1. So the problem itself said to use the definitions to find the exact value. And I did that, but I'm also showing how you could check it and maybe even sometimes just do the problem by typing it on a calculator. Okay, so let's go back over to the tablet again. All right, so I did it a couple of different ways. And so then I can go over here and put in a 1. And it's happy, etc. And so cosine was the 0 value, tan would be 1 divided by 0 would be undefined, as I did before. So let's go ahead and put those in. This is a weird thing on this calculator, but I can still do that. And then it says the solution is undefined is choice A. And that was it. So certainly if they give us this S symbol for arc length instead of using theta, I'm literally suggesting just think of that in terms of theta, because that's the way I defined it in the first place. And then these are all just sine of these radian measurements. And you can define those as being the point on the unit circle, either the y value, the x value, or some fraction of those or something like that. All right, so this was the first problem in the exercise set. Maybe we'll skip ahead to problem 10, see what that looks like. Use the unit circle along with the definitions of the circular functions to find the exact value for the function at the right, given that s equals 23 pi over 6. And then there's a question to do problem 18 after this one. Yeah, that shouldn't be a problem. I don't know what it is, but we'll find out. Okay, so again, the first thing I would suggest that we think about here is that you're considering theta equal to 23 pi over 6. And so we'd really, the hard part would be to figure out where the heck is that on the circle. And then we can, from that, just figure out the x or the y value of the point using our little triangle math things that we've done before. And so I also, in order to evaluate the secant, I want to remind everybody that secant is 1 over cosine. So this would be equivalent to 1 over the cosine of 23 pi over 6. And the cosine would be the x value of the point at that place. So one of the ways I can make this a little easier is I can recognize the portion of pi this is. So 23 over 6 as a mixed numeral, if I divide 6 into 23, it goes 3 times. That would be 18. And then that leaves 5 more. So this is 3 5/6. So this is 3 5/6 of pi. Now you don't have to do it this way. This is how I think about it. That's the multiple of pi we have here. So if I think again about my unit circle, and I'll use this nice line on the screen here to help. Then remember, you start at 0. Going this way is the positive direction. When you get over here, you're at pi. When you get back to where you started, you're at 2 pi. if you keep going around, over here is pi over 2. Over here is 3 pi over 2. Again, this is if you're going in the positive direction. Well, if I go around the circle twice, if I go around once, I get 2 pi. If I go all the way around again, I'll get to 4 pi. And then after that, I would get to 6 pi as I just keep going around. So I can ask myself, well, where is it when I'm 3 and 5/6 pi? That's almost 4 pi. So if I go around once, I get to 2 pi. If I start to go around again, then after pi, I'll get to 3 pi. And so that after I get to 3 pi, I want to add 5/6 of pi. So I'm going to draw in some angles. That was a bad one on the last one. There we go. Maybe more like that. So I chopped this bottom semicircle into sixths so that each one of those is now 1/6 of pi. So when I'm at 3 pi here, after I've rotated around 1.5 times, then this is 3 and 1/6 pi. This is 3 and 2/6 pi. This is 3 and 3/6 pi. I didn't mean to do that. I'm going to select anything. 3 and 4/6 pi. And then this line would be 3 and 5/6 pi. And then I'd have 3 and 6/6, which gets me to 4 pi. So 3 and 5/6 pi is 1/6 less than 4 pi. And so that means when I'm at this angle, I'm talking about this point here. So that point there is 23 pi over 6. And so I can now recognize that this is exactly the same as the angle negative pi over 6. That if I go backwards 1/6 pi, I'll get to that same place. So since 2 pi is all the way around, one of the things that people will do is they'll just subtract 2 pi until they get to a number that's less than 2 pi. So here, just let me show you one other way you could have possibly done this a little bit more mathematically. If I have 23 pi over 6, well, as I said, 6 goes into 23 more than 3 times. So this is more than 2 pi. So I could subtract 2 pi from this and it won't change the angle. And if I do that in terms of 6, 2 pi is the same as 12 over 6 pi, because the 12 over 6 is 2. And then that would give me 11 pi over 6. And so then if I go 6 over 6 pi, that's to pi, and then 5 more, I end up in the same place that I am here. But here, 11 pi over 6 is the angle that's within one rotation instead of having to go around more than once. All right, well, one semicircle around is 180 degrees. So if I'm only down 1/6 of a semicircle, then this angle here is 30 degrees. And that means that my reference angle, as we discussed before, a reference angle is a 30-degree angle. That means the degree angle up here is 60 degrees. So we have a 30, 60, 90-degree triangle there. So I'm going to blow this up a little bit. Let's change colors so that we can follow along with that. So that angle, that triangle that we have there that gets me to that point, that's this triangle here on our diagram. And there's the point in question. So that's a 30, 60, 90-degree triangle. And the side ratios that we want to remember in a unit circle is the radius is 1, the small side is 1/2, and the longer side is square root of 3 over 2. That's every time you have a 30, 60-degree triangle where you have 1 for your hypotenuse, which will be the radius of our unit circle. Okay, so that means that the coordinates of this point well, the x value is this distance here, and it's to the right. So that's square root of 3 over 2. And the y value is this distance here, which is 1/2 going up and down, but it's down below the x-axis, so the y value is negative 1/2. So that means if I take the cosine of 23 pi over 6, I want the x value, which is positive square root of 3 over 2. So that means this cosine here is the square root of 3 over 2. So to take the secant of that, I have to flip that upside down. So the secant of that would be that fraction flipped, which is 2 divided by the square root of 3 instead of the square root of 3 divided by 2 because it's flipped. Now it does say to simplify our answer, include any radicals using integers or fractions. They may even want me to rationalize that denominator. I don't know if they want that or not. We can try it both ways and see if they give me credit both ways or one way or another. But ultimately the answer is 2 divided by the square root of 3. So let me pause there and see if there are any questions about how I came up with that.
I got kind of lost after we found 11 pi over 6 when you got to the 30, 60, 90 triangle. Would you mind going over that again?
How we got the 30, 60, 90 or after we got the 30, 60, 90?
After that, I guess is what I mean.
Okay, so I have the 30, 60, 90 sketched in there on the circle. And so that I'm sketching in because the goal to evaluate a trig function of an angle is to figure out the x and the y values of the point on the unit circle at that angle. That's the goal. We want to know what's the x and the y coordinates of that point because that's how we define the trig functions. And so the x and the y values of that point will be the sides of the triangle positioned in the correct quadrant. This is in quadrant 4. In quadrant 4, you may recall from before that all the x values are positive and all the y values are negative. But the side lengths of that triangle will tell me what the x and the y values are. The x value is the value that's the bottom of that 30, 60, 90 degree triangle, or this side here. And in a 30, 60, 90 degree triangle, that's the side opposite the 60 degree angle. That's square root of 3 over 2. So is that where I lost you?
Yeah, I think I understand now. Thank you.
Okay. And the y value is the up or down vertical line here. That's opposite the 30 degree angle in this situation. And that means that has a length of 1/2. The other kind of a triangle we might have to use is the 45 degree triangle, 45, 45, 90. And that would happen if it was like some quarter of pi instead of a sixth of pi or something. Okay, so I get 2 divided by the square root of 3. So let's go back and put that in. See if it takes it like that. 2 divided by square root of 3. Yep, so it didn't even force me to rationalize the denominator. It just wanted the exact value with the root. Other questions at all about how I did this problem number 10 from the practice problems? So there's work to do here, and this is really going to make us understand the circle inside and out. But I'm just pointing out that their discussion in 3.3 about how this is an S and this is a circular function, we don't need to do any of that. This is just sort of a bunch of stuff that we've been doing for the last 2.5 chapters up till now. So there's a lot to do here. This is not simple, but we don't need to think about it with all the confusion of the way they're talking about it in 3.3. With the questions at all? All right, so the request was to do, I think, 18 next, so let's try that. Well, that's not a very fun looking diagram. Okay, so now we have the problem. It says the figure to the right. Can I zoom in on here? I can zoom in a little bit. So I can zoom in when we need to look at this to do something because it's kind of ugly looking. But for now, let me read the problem. The figure to the right displays a unit circle and an angle of radian 1 of 1 radian. That means the arc length up to that angle is 1 along the circle. The tick marks on the circle are spaced at every 2/10 of a radian. So we can see 0.2 radians, 0.4 radians, 0.6, 0.8, and then you're up to 1 radian when you get to the pink line there. Use the figure to estimate the value of the cosine of 0.4. All right, so I'm going to blow this up a little bit, and then let's see if I can take a picture like that. That worked. Okay, so we want to find cosine of 0.4 approximately. Well, again, this is theta in radians, or they're going to talk about the arc length because they've measured the arc length. So 0.4 is right here. And so this is the point they're talking about on the unit circle when you're that far around. And cosine will be the x value of that point. And so the x value, I would go, looks pretty close to this dotted line. So if I go straight down from here, the x value is going to be around there. And I believe that's where x is equal to approximately 0.9. How do you feel about that? So that's the answer. They asked us, what is cosine of 0.4? We have to find where is the radian measurement of the angular place to get to 0.4. Well, in this case, they just marked off different spots on the circle so we could see where 0.4 would be. Remember, up here is pi over 2, over here is pi, but pi is a number, 3.14159. You can see here's 3 right here. So you go a little bit past 3, and then you get to 3.14159. Well, somewhere as you're going around the circle, you're at 0.4, and they've marked off these little spaces around the circle so that we could find where that radian measurement was. And then the cosine for that radian measurement is the x value of the point that's there. And then we would just look that up by looking on the x-axis and saying, I think that's about 0.9. So round to 1 decimal, so I would just put in 0.9. Are you satisfied with that, Gene? Anybody else want to ask a question about this example number 18? There's definitely a lot to think about here, but I think by thinking about these problems, it'll really help us because that'll improve our understanding about what these trig functions are really doing and how they work. And that'll make it easier for us to use them in word problems. I think in 3.4, we might have to do a little bit of word problem action. I'll save that for Thursday. What if we had looked at the example here? I wonder what that looks like. View an example. So in this case, they had 2.2, and they would have said cosine S equals X. So that means it's the X coordinate of the endpoint. So they're at least trying to say that. And so, but they're not drawing that on the picture or showing how they got the negative 0.6. So that's kind of, it's the right idea, but they didn't follow that up with a diagram of what they're doing. So I think it's helpful, but not ideal. Better than nothing. All right, maybe we have time for one more at least to take a look. So let's see, you'll skip down a little bit more. What if we jump down to like 35? I don't know what's there. Let's find out. So it says, find the exact values of S in the interval 0 to 2 pi. So that means only one rotation around the circle. Satisfy the given condition that the cosine value of that S after you square it equals 1/4. So this one's definitely a little harder, but we're like 35 problems in here. But again, we don't really need any of their discussion, I think, to do this, except we have to know that when they do S, I'm going to remind us this just means theta. Whoops, I meant to do that with my pen. Okay, so again, I'm just going to have us think that this means cosine theta squared equals 1/4, and we want to find theta in the 0 to 2 pi range. That works. That's a solution that makes that condition true, given that satisfies that condition. Well, since it's squared, the first thing we would want to do is figure out, well, what is the cosine theta value? And so I would square root both sides. And you may recall when you're solving and you square root both sides, because you have a square you're getting rid of, you have to use a plus or minus. So if I do that, then I just get the cosine theta, or of S, or whatever you want to call it. And if I take the square root of a fraction, I can square root the top and the bottom separately. So this is plus or minus the square root of 1 is 1, and the square root of 4 is 2. So I have plus or minus 1/2. And the thing to remember is that cosine of theta, so that means that these are the x values of points on a unit circle. Cosine of theta is the x value of a point on a circle, and we have to figure out which theta would make the x value turn out to be plus or minus 1/2. All right, so looking at my unit circle here, where is the x value equal to plus or minus 1/2? Well, here's where x is 1/2, and here's where x is negative 1/2. So I need points on the circle that have those x values. I can go up here. There's a point where the x value is 1/2. And let's look at that more carefully. If I'm imagining what the theta would be to get up there, because I'm supposed to figure out what's theta in radians, what's that arc length? Well, I know that the bottom side is 1/2. I know that the hypotenuse side is 1. So that means this one is square root of 3/2. This is our 30, 60, 90 degree triangle. That means this degree here is the long one. That's 60 degrees. And so that means theta, I'm just using degrees because we did that most comfortably, but they're going to want that in an S, in a radian measurement. And so 60 degrees is 1/3 of the way to 180. So that means this is pi/3. So this is at an angular measurement of pi/3 if I'm there. But if I keep going around the circle, when I get above this point here, then I'm going to have another point that could produce a cosine of that angle to be satisfying that condition because we want where x is positive or negative 1/2. And so when I'm at negative 1/2 and I'm at this angle, well, I also have a 30, 60, 90 degree triangle. I've gone another 60 degrees over. So this was pi over 3 to get to there. Then this is at 2 pi over 3. Well, if I keep going from there around the circle, then I will get down to a point down here where the x value is still negative 1/2. And again, I have 1/2 is the length here. And so this is 3 pi over 3, which is just pi. And if I go another pi over 3 down, I get 4 pi over 3 to get to that point on the bottom there. I'm finding the radians that I have to go around to get those x values. And then lastly, if I keep going, because I'm going between 0 and 2 pi, if I keep going around, then I'll get to this other point over here where the x value is positive 1/2. And that's another pi over 3 increase. So that's 5 pi over 3. And if I go the last 60 degrees, I would be at 6 pi over 3, which is the same as 2 pi, one full rotation all the way around. And that's the limit of the range that they're asking for. So it looks like I can get either an x value of positive 1/2 or an x value of negative 1/2 in one of those 4 locations. Pi over 3, 2 pi over 3, 4 pi over 3, or 5 pi over 3. And those are the S or the radian theta measurements that will satisfy this equation, because then when I plug those in, I get an x value of plus or minus 1/2. And then when I square it, I get positive 1/4. So I would put those in. So what did I have there? I had pi over 3. And I'm supposed to separate that by a comma. And then I had 2 pi over 3. And then I had 4 pi over 3. Whoops, I need a comma there. And then lastly, I had 5 pi over 3. I think that's what I had. 5 pi over 3. And that's where we will stop because we are out of time. So anyway, we got to do several problems. So I'm going to stop recording here.